Okay, today we're going to look at two of the terrestrial planets, Mercury and Venus. And if we recall the comparison of all the planets with the curvature of the Sun, we see that compared to the Sun, Mercury and Venus are quite small, and compared to the Jovian planets as well. Venus in this diagram looks approximately the size of Earth. Well, they're terrestrial planets, and that means they're like Earth, at least in density. Here are some particulars about Mercury. There's no tilt to Mercury. It has a prograde orbit like the other planets. Its rotation is also prograde, 59 days of rotation, which is 2/3 of its revolution period. This revolution period is 88 days, and it turns once on its axis in 59 Earth days. Venus has no tilt, has a retrograde rotation, even though it's prograde revolution. Retrograde rotation in 243 days, which is approximately on the order of its revolution period. Its revolution period is 225 days. So you could say to some extent it might be gravitationally fixed towards the Sun, but most likely this is a remnant of some other occurrence, like maybe a collision in the past. Earth has a tilt, 23.5 degrees, prograde rotation in 24 hours. And Mars has a 24-degree tilt, prograde rotation in 24.6 hours. So in terms of tilt and rotation, Mars and Earth are very similar. Mercury and Mars have more eccentric elliptical orbits, and we'll discuss the consequences of Mercury's elliptical orbit today when we look at the more particulars about Mercury. Here's a picture of the Sun, Mercury and Venus, and as planets, as interior planets, inferior to the Earth, Mercury and Venus can only be found relatively close to the Sun. So if you're looking for those planets, you would not find them necessarily in the middle of the night long after the Sun is set. So you're either going to find them close to the setting of the Sun at night, at dusk, or close to the rising of the Sun at near dawn. So within a few hours of the location of the Sun. In fact, Venus, being a very bright object, the third brightest object in the sky, is known as the morning star or the evening star because it's relatively close to the appearance or disappearance of the Sun. It can be seen to within 3 hours of sunrise or sunset. Mercury is hard to see because it's so close to the Sun, and hence it's not as bright as Venus to begin with, and also it's closer to the Sun, so you have to look for it right at sunrise or sunset. Here are the greatest elongation angles for Mercury and Venus. For Mercury, it's 28 degrees, which means your greatest chance to see it furthest from the Sun is at an angle of 28 degrees. We can imagine that there's a right angle here between the Sun and Mercury and the Earth, and hence at this point Mercury would appear to be half lit. So half of it would be lit and the other half would be dark. But it's at its greatest angular distance from the Sun, 28 degrees, which is approximately 2 handspans. If each handspan is about 15 degrees, 2 handspans from the Sun. And in terms of angular expanse over the course of a night, one handspan represents 1 hour of movement. So at its greatest elongation, Mercury would be about 2 hours from the sun, either before sunrise or after sunset. For Venus, it's about a 47-degree angle, so that's 3 handspans, or about 3 hours lag or lead to the sun. So your best chance would be 3 hours before sunrise if it happens to be at that point, or 3 hours after sunset. Being close to the sun, at least 40% of an astronomical unit, Mercury will sometimes be on the same line of sight between the Earth and the sun, and hence transit actually the image of the sun. This occurs about 13 times per century for Mercury. Mercury and Venus are the only planets that can do this because they're inferior planets. They're interior to the Earth's orbit, so it's possible they can be in that plane between the sun, the Earth, and the ecliptic plane in between. So they're the only planets that can do this. The terrestrial planets are more dense than the Jovian planets, and a lot of this has to do with the fact that they due to their differential cooling, they actually have a lot heavier elements on the interior. They can have metallic or iron type elements on the interior. In fact, the density of Mercury, Venus, and Earth are quite similar, on the order of 5 grams per cubic centimeter. However, Mars is considerably less dense than these. Mars is on the order of 3 grams per cubic centimeter, suggesting a different composition. Mercury's core is the largest proportion of its interior, probably making up most of its interior. And Venus's interior is believed to be very similar to the Earth's, a molten type core with a mantle, and well, that's pretty much it. Probably in about the same rough proportion to its size. Here's a look at Mercury. Looks a lot like the Moon, except that the craters in proportion to its total size are much smaller, but the Moon is much smaller than Mercury. So it's the same kind of craters, and you see the same kind of effects. You can see rays extending from these craters. You don't see Maria. Mercury is the nearest planet to the Sun, 0.39 astronomical units. And like the messenger god, it's named for the fast messenger god of the Romans. And partly that's because it takes so little time for it to actually revolve around the Sun. It only takes 88 days to go around the Sun. So approximately 3 Earth months for Mercury to go around the Sun. So in the course of a year, Mercury will go around the Sun 4 times, while the Earth goes around the Sun just once. These are pictures taken by Mariner 10, which is the NASA's probe to look at Mercury. So we're just looking at the surface. Pictures taken in the 1970s by Mariner 10. Here's a look at the surface. You can see the craters and smaller craters, some of them impending on the larger craters. And to me, give it a little bit of color, to me it just kind of looks like boiling spaghetti sauce, if you will. As you're looking at this, it's boiling up and just looks like spaghetti sauce. Maybe it's near lunchtime. Here's an interesting feature on Mercury. We can see this crater. We can see this kind of bend here on the surface. This indentation here called a scarp. Here's another look at a scarp. Here this crater, and then see this indentation here of the scarp. And that's a feature that's on Mercury that you do not find on our moon. More on what that is in a moment. But here's a look at more pictures taken by Mariner 10 of these craters. And you can see a lot of them are kind of double craters as well, so suggesting that maybe upon impact the Mercury was kind of more of a molten type world at that point, and these plops of these impacts were creating more than just the initial crater, but double craters where you would have a recoil effect. Another look at the surface of Mercury. Here's another look at those kind of craters that we're just talking about. You can see an inner radius to this crater, and this one over here. Also, these craters are elongated, so that's suggesting that these impacts were kind of more transverse, not directly onto the planet in this particular case, but kind of grazing, and hence causing a more elongated impact zone, but still with this double crater effect. So here's a pop quiz. Looking at the left and looking at the right, which of these is actually spaghetti sauce, and which of these is actually the planet Mercury? You got 5 seconds. 5, 4, 3, 2, 1. Well, they look very similar, but of course Mercury is on the right and the left is spaghetti sauce. Here's a comparison of Mercury to the Earth. Revolution of Mercury is about 3 Earth months, or 88 days of revolution to go around the Sun. That means Mercury will go around the Sun 4 times in the time that the Earth goes around the Sun once. Radius of Mercury is about 38% that of Earth, so about approximately on the order of 40% of Earth's. Mass is 5.5% of Earth's. Surface gravity is about 40% that of Earth. So, given that Mercury will go around the Sun 4 times for every time that Earth goes around once, radius is about 40%, gravity is about 40%. We'll say on a scale of 1 to 10, Mercury is about a 4. Here's how Mercury would look if you looked at it through a telescope from Earth. And it's looking at a crescent phase, which is, if you're looking at Mercury, that's probably one of your best bets, is that it's going to be looking like a crescent, because you'll be looking at it while it's on our side of the Sun, and hence then it's either at best half lit or about crescent. If you're looking at it as it's moving away from us, you might see it go into the gibbous phase, but it wouldn't be quite as bright at that time. But here, as you're looking at it in this crescent phase, you look along this terminator line, you can see more of the crater features, and so that's your best bet to see some features on Mercury, is to look at this time in this crescent phase and look at that terminator where the shadows will help let you see some of the features on the surface. We can get an idea of how fast Mercury is rotating by using the Doppler shift. If you send radar and you hit the planet, and if the planet is turning, then the part of the planet that's turning towards you is going to have a higher frequency because it is approaching you. and the part of the planet that is receding from you is going to have a lower frequency because it is receding or redshifted in a sense away from you. So you have a blue shift on one side, a red shift on the other side for the radar signal, and depending on how much it's shifted, you can figure out how fast it's moving on either side, and hence from this data figure out how fast it is rotating with respect to you. Same sort of effect is used to figure out the rotation speed of storms, and hence you might be able to recognize a tornado using Doppler radar because you would recognize that there was rotation in that storm. Well, with this data, we know that Mercury is spinning very slowly. In fact, it turns once on its axis every 59 days, which is on the order of its revolution period of 88 days, but not exactly. So it's not totally fixed to the Sun. And part of this has to do with the fact that its orbit is elliptical. It's more elliptical than the other planets, except for the dwarf planet Pluto. But the other main planets, the 8 planets, Mercury has the most elliptical orbit, and hence it's sometimes going faster and sometimes slower around the Sun, and this speed difference causes it to have a 3-to-2 spin-orbit resonance. So that's its spin is 3 times, while its orbit is 2 times. If we look at this, how this might occur as it's going around the Sun, imagine that you're facing the Sun on day 0, so that's noontime. The Sun has just crossed your overhead meridian on day 0 at noon. You start to turn as you're revolving, but as you revolve to the other side, so you're on the other side of the Sun on day 44, you really haven't turned all the way around, because as you're turning, you're revolving at the same time. So you're actually facing this direction. You're not facing the Sun yet. And finally, when you get to day 59, you still have been kind of facing away from the Sun for some time now. So you have not completed a revolution with respect to the Sun. You continue to turn on your axis. You've completed one rotation, though, on your axis. You can continue to rotate now, and after another rotation on your axis, you're facing away from the Sun again. You're still facing away from the Sun. So you rotate again. You continue to rotate once on your axis, and after 2 years, you find you've finally reached the position where the Sun will cross your overhead meridian again. So between one crossing of your overhead meridian and the next crossing of your overhead meridian, it has been 2 years. 2 Mercury years. So for one noon to the next noon is 176 Earth days, or 2 Mercury years. So 1 Mercury day is 3 Mercury rotations and is equal to 2 Mercury years long. A Mercury day is longer than the Mercury year. In fact, it's 2 Mercury years. Because the year is the time, Mercury year is the time it takes to revolve around the Sun. And this is just a combination of a tidal influence from the Sun and the eccentric elliptical orbit. If the Mercury orbit were totally circular, then it would be tidally fixed to the Sun, and hence its day would be equal to its year. But that's not the way it is. Looking at the surface of Mercury, again, it kind of looks like the Moon, and this is a composite picture. Pictures taken by Mariner 10. So it's got very similar features to our Moon. No atmosphere. Here's a look at a particularly large crater on Mercury, Chloris Basin. Temperature range on Mercury between day and night. Daytime is about 700 Kelvin, which is about 800 degrees Fahrenheit. Nighttime is 100 K, which is about minus 280 degrees Fahrenheit. So between day and night is a shift of more than 1,000 degrees Fahrenheit. So it gets extremely cold and extremely hot. The polar ice caps, which might be in shadow all the time, will be very cold, 125 degrees Kelvin. So there's a great possibility that there will be water ice still remaining in the polar ice caps in shadows of craters that never see the light of the sun. And because of that, and because there's no atmosphere, they remain cold, and hence there's possibly water on Mercury in those shadows of those craters. Point is, though, Mercury doesn't quite get as hot as Venus because it has no way to retain heat with an atmosphere. So in the daytime it's very hot, and at nighttime it's very cold. It's got some weird terrain. As we said, it's got these double craters that kind of look like something just plopped right into a relatively molten type material. And it's got these rippled areas that we mentioned before called scarps. And here's that relatively large crater called the Chloris Basin. The Chloris Basin is an immense bullseye crater with an interior crater as well, and another interior crater. So it's a kind of a rippled effect on this crater. And you have the secondary craters as well around the perimeter due to the ejecta causing these secondary craters, debris from the first impact. Here's a look at the scarp wrinkles, and basically this is the idea of a somewhat molten planet that in which the interior kind of cooled faster than the crust, and hence you've got this crust that's cooling with this inner part cooling, and hence it's kind of wrinkling on itself. And this is a feature that you see on Mercury, but you do not see on our moon. So our moon did not have this same kind of cooling effect. So the terrain is similar, but there are no scarps on the moon, and on Mercury there are no marias. So that's major differences between the two landscapes. Mercury has no atmosphere because of its low gravity, only 40% that of Earth, and it's high temperature in the daytime. So any kind of light elements, any kind of volatile elements, any kind of lighter gases will be long gone because they'll be given enough energy to escape the weak gravity. So this variation between hot and cold is the greatest variation among all the planets. No other planet gets so hot and then so cold with this more than 1,000 degrees Fahrenheit temperature difference. So it's quite inhospitable to life as we know it. And not only that, with no atmosphere to speak of, there's no protection between meteoroids and solar radiation. So there's micrometeoroids constantly bombarding the surface, and solar radiation constantly bombarding the surface. So there's no possibility that life could live there. So it's a geologically dead planet as well. Nothing going on in terms of volcanoes at this point, not showing any sense of erosion. There's no erosion factors to take place. There's no atmosphere, there's no water, nothing to take place except for the impacts of micrometeoroids, but that would be the only thing to change the surface of the planet. It has a weak magnetic field, which is a little bit surprising that it has a magnetic field at all, since it spins so slowly, which kind of means that its interior must have a lot of iron, and suggesting that its molten interior is much larger than that of the Earth's, hence allowing it to have this 1% of the Earth's magnitude of magnetic field. So its interior is differentiated into a core and a mantle, and the core makes up a larger percentage of its interior than the core of the Earth, still giving it a very high density in terms of a terrestrial planet. Recently, in the last couple of years, NASA has sent a new probe to Mercury, and it has taken new pictures. So here are the latest pictures by the Mercury Messenger, and man, that's a cool car. The Messenger is, I mean, any way you look at it, it's pretty awesome. You know, it's got these features, these scarps. Alright, so that's not the Mercury Messenger we're talking about. We're talking about pictures that look like this. And that's pretty cool too. These are high resolution pictures of the surface of Mercury. You can see how beautiful it is with these high resolution pictures. You can see more of the detail of the craters and the rays extending from these impacts on Mercury. Beautiful. The surface looking like the moon, but evidently, obviously, there's no life on Mercury, so there's no possibility that there's life on Mercury, except for these communications that we keep on seeing, these communications from possibly surface life on the planet. Beautiful pictures of these craters and more scarp-like features of these ripples on the surface, these folds. Okay, let's look at Venus, which is a closer planet to us. It's the brightest planet in the sky, the third brightest object in the sky after the sun and the moon. Often called the morning star or the evening star, because being a bright star, you definitely see it at dusk or dawn. And even though the sun's light still might block out other stars in the sky, this would be bright enough to still see it in that occurrence, and hence it's called the morning star or the evening star. Due to its brightness, it was named after Venus, the Roman goddess of beauty. And if we bring in Venus, the Roman goddess of beauty, we can see some similarities. They're both quite thin. I'll leave it at that. Both quite thin. Here's an ultraviolet image of Venus showing a lot of its cloud cover, taken by Pioneer in 1979. Venus' brightness to us is caused by it's got a real high albedo because the 60% of the light hitting its clouds are reflected, and we get a lot of that reflected light then coming towards us. Its closeness to the sun means that it's going to get more insolation than, say, other planets, the outer planets. Hence, it has more light from the sun, and that would make it brighter, as it appears to us. It is, in fact, the closest planet to us. So as far as from proximity, it will be brighter as we see it. And in fact, as terrestrial planets go, it's larger than Mercury or Venus, or Mercury or Mars. So as terrestrial planets go, it's got more surface area to give us more light. So all these are major factors, and hence making Venus predominantly much brighter than any of the other planets, and like we said, the third brightest object in the sky. Much brighter than any star. We cannot see the surface of Venus from Earth because of a thick cloud cover that covers the whole planet. And so you can only see, at best, the thick cloud cover. So any telescope from Earth cannot see any geological features on the surface of Venus. Here's a look at the high cloud cover on Venus. Venus's spin is retrograde, which is clockwise, which is opposite that to most of the planets. Most of the planets rotate prograde, but Venus is retrograde and Uranus is retrograde. And the thought is that at some point something must have collided with it to give it this slight spin in a backward manner. Its axis of rotation has almost no tilt, so it's tilted straight up and down. Here's an ultraviolet image of Venus from the Hubble Space Telescope in 1995. Venus completes one revolution in 225 days, which is a period very close to its rotation period, which is 243 Earth days. So they're very, very similar. Rotation slightly longer than its revolution. We can see these high cloud patterns in ultraviolet light. These clouds contain sulfuric acid, so Venus would not be a very fun place to live. For one thing, is it rains sulfuric acid. Venus's atmosphere is much more dense than Earth's. The atmospheric pressure is about 90 atmospheres, which would be equivalent to if you were to dive to 1 kilometer under the sea. That would be the pressure that you would feel. We feel 1 atmosphere of pressure being on Earth, which is 15 pounds per square inch on every square inch of our body. If you were on Venus, you would feel 90 times that. So even though we are used to that and we're quite familiar with 15 pounds per square inch, we know that when there's a weather system that changes the pressure just slightly, just a few percent, you can feel that. Maybe you'll feel that in your sinuses, and you might feel not so good that day because of the slight air pressure between what we feel from a day-to-day basis. But if you've suddenly felt 90 times more air pressure, so instead of 15 pounds, you would be more than 1,000 pounds per square inch, you would be crushed. So on Venus, it would be inhospitable because you'd be crushed under all this atmosphere, this 90 atmospheres of pressure. So not only is there sulfuric acid coming down, you have this crushing effect of its atmosphere. Here's a look at its atmosphere. There's extra thickness to it because there's so much of this atmosphere, considerably thicker than the Earth. It's composed mainly of carbon dioxide, 96%, and nitrogen, 4%. It's similar to the kind of atmosphere Earth would have if all of our carbon dioxide from limestone and the oceans were put out into our atmosphere. This carbon dioxide causes a runaway greenhouse effect, so insulation that makes it through the clouds gets trapped by this very thick carbon dioxide layer, and hence it maintains a very hot surface. There's no water vapor at all in Venus. Venus is 0.72 astronomical units from the Sun, so it's only about 30% of the Earth's sun distance from us. So it's the closest planet to Earth at its inferior conjunction. As bright as Venus is, we only see it half lit at greatest elongation, because at greatest elongation there'll be a right angle between the Sun, Venus, and the Earth, and so at that point you would see just half of Venus being lit. Now you could see a gibbous phase of Venus as it were further back on that orbit, but that would mean it was closer, as we see it, to the Sun. Here's a nice picture showing an occultation of Venus with the Moon. If we were to look at the surface of Venus with radar, we can actually see features of the surface. In other words, radar can make it through all this cloud cover and actually see features of the surface of Venus. We find that the radius of Venus is 95% that of Earth. Its mass is 82% that of Earth. So it's truly a sister planet. It's on the order of the size of Earth. Density is similar to Earth's. Gravity is about 90% of Earth. So if you went to Venus, you would weigh 10% less. So a good diet plan would be not to change your eating habits at all, just to jump on a spacecraft and fly to Venus, and you would immediately lose 10% of your weight. So that'd be a great diet to be on, except for the fact that you'd be subjected to sulfuric acid rain, and you'd be crushed to a pulp by 90 atmospheres of pressure, and the temperature would be 750 degrees Kelvin, or about 900 degrees Fahrenheit, so it wouldn't feel too good. But at least you wouldn't have to worry about your diet. Yes, it is indeed the hottest planet, 730 degrees Kelvin, on the order of 900 degrees Fahrenheit, or 850 in this figure here, due to a runaway greenhouse effect, the kind of greenhouse effect that can't be stopped, too much carbon dioxide. This keeps the temperature hot all the time, and because of the atmosphere, it keeps it hot all the way around the planet. The atmosphere helps retain all that heat all the way around the planet. So unlike Mercury, which is really hot during the day and really cold at night because there's no atmosphere to mitigate those effects and maintain it, Venus is hot all the way around. It's hot all the time, no matter where you go on the planet. It's the hottest planet. Here's a Magellan map taken by radar in the early 1990s. NASA sent another probe to look at Venus, and using radar, it mapped all the surface of Venus in many flybys, and hence we actually know what the surface kind of looks like through this radar map of Venus. Here's an equatorial view of Venus. And here's a north polar view of Venus. And we can see what looks like a lot of impacts and some volcanoes. If we were to look at Earth with radar, we could see all the features, geological features of Earth, and it would look like this map as we see here, which is a Mercator projection of the radar map. And so you could also see the mountain ranges underneath the ocean. You would see all the mountain ranges on the continents and the oceans, the depressions, the trenches. You see all that on Earth. If you were to look at the same thing with Venus in a Mercator type projection, you would see similar things. You would see mountain ranges, you would see depressions. Here you would see what would appear if there were oceans on Venus. You would see what would be covered by those oceans. And you see two major continental land masses, Ishtar Terra and Aphrodite Terra, named after female characters, because Venus, of course, is regarded as a female planet. So it's composed of smooth plains and has these two continent-sized highland regions, Ishtar Terra and Aphrodite Terra. Here's another look at it, enhanced with color. Of course, these depressions are not indeed oceans because there is no water on Venus. It is just where water would be if there were water on Venus. Here are some Venus surface features taken by radar, and you can see that Venus's surface is composed of black hot rock, kind of flat type rock, and you can have a lot of volcanic features on Venus as well due to volcanic lava flows. You can see these pancake-like lava flows on the surface of Venus. Indicating viscosity was high when this lava flowed, forming these flat pancake-like features before they cooled, making it dome-like. Kind of looks like you had a frying pan and you were making these for dinner. There's more pancakes. Here's some arachnoid formations on Venus. They're basically, with Venus with all this volcanic type surface, it's sort of glassy in a sense. If you have this, it's more amorphous type rock, and when you actually have the impacts of meteoroids on the surface, it crashes through this glassy type rock and forms these images that kind of look like spiders with a body and legs extending outward, but it's truly a feature of craters hitting this kind of glassy type rock. We call this effect or this kind of image a coronae on the surface of Venus. In fact, this one actually is probably not an impact, but it's probably just a lava flow that instead of exploding, imploded and left its a corona type depression in the middle of this lava flow. Venus has many volcanoes, and here's one of the larger ones, Sapis Mons. In fact, Venus has 167 volcanoes larger than 100 kilometers in diameter. The Sapis Mons probably is the largest. The largest one in the solar system is actually volcano is actually on Mars, but Venus has 167 volcanoes that are almost on that size as being the largest type volcanoes in the solar system. Earth, in comparison, only has one volcano with this kind of diameter, 100 kilometers in diameter. And Venus has over 50,000 smaller volcanoes, so it's a very volcanic world. Most of these volcanoes are shield-like volcanoes, which means that they have many slow lava flows over time, and it kind of makes the terrain look more like a shield as opposed to a more violent tephra-type lava or volcanic explosion, which would be more of a peak-type, a cinder cone-type volcano. But these are shield volcanoes, which just have these slow lava flows, the kind of things that you would see in, say, Hawaii, which has those kind of volcanoes. Here's Mons on Venus. Here's the Tick volcano on Venus, because it kind of looks like a tick that's walked across the surface and walks off. Here's the Fosse impact crater, and this kind of impact you can see shattering through that rock, and you can see the ring effect of that impact. Here's the Meade impact crater, a very large impact, and also it has kind of a double crater impact effect as well. Very large impact, 280 kilometers in diameter. This is the largest one on Venus. All Venus impact craters are large in size. This is because in order to survive that 90 atmospheres of pressure and this thick atmosphere, it has to be large to begin with, because any kind of small meteorites coming in are going to be burning up in that atmosphere and will never make it through. So in order to survive that kind of atmosphere, you have to have large objects to begin with. Here's the Mona Lisa crater. ,86 kilometers in diameter. Here are some impact craters on Venus, and you can see to me it just looks like bullets going through glass. I mean, you got this amorphous type rock, which is what glass is, and these high velocity meteorites have come in to make meteorites and just hit and shattered through the glass. In fact, if we compare this to actual bullets through glass, we can see that's what a bullet through glass looks like. And we'll change all these to bullets through glass, and it looks like what a bullet through glass would look like. You have a major impact crater in the middle and a lot of fracturing around that, and then fracturing arachnoid type radially outward beyond that. So bullets in glass. In fact, this is so alarming that it's kind of neat. And it kind of makes you think, yeah, there must be some kind of law enforcement on Venus, because this high resolution picture shows a police line. Here's some lava flows that kind of made some interesting figures on the surface of Venus. This kind of looks like a lizard outflow channel. The Russians sent many probes towards Venus, and about the first 10 or 11 of them malfunctioned, either on their way there, near Earth's atmosphere, or when they reached Venus's atmosphere. At that time, it wasn't known all these features about Venus's atmosphere, that sulfuric acid, 90 atmospheres of pressure, how hot it is, all those things. It was believed that Venus might be a world like the Earth. So when they first started sending probes there, they started burning up, they started malfunctioning, and finally, after many efforts, many years, they finally got some probes to land, and they're able to monitor the lighting effects on Venus and saw that they possibly could take pictures. On the surface of Venus, there's enough light that it kind of looks like Earth on a very cloudy day, and so they were able to take pictures. And so they took some pictures, and they saw that the rocks were kind of flat like plates, like we said, these glassy type rocks, volcanic type rocks, and they only took a few pictures before their spacecrafts were crushed by the great atmosphere of Venus. So they got a couple pictures out of it. Here's another look. You can see the glassy effect of these rocks on the surface of Venus. United States sent a probe to Venus and actually landed on Venus, but didn't have a camera. Forgot the camera. No, actually, at that time, they didn't believe that you could actually take pictures on Venus, so they didn't worry about putting a camera on the probe. That concludes this lecture on Venus and Mercury, the first half of Chapter 6.